Hello, students. Today we're going to wrap up section 8.2. Let's take a look. This is part 2, of course. Example 4, repeated use of integration by parts. So we're going to find the integral of x squared sine of x dx. As the example suggests, we are going to do more than one integration by parts process. Letting u equal x squared, letting dv then equal sine of x dx will lend itself nicely to, again, using the appropriate theorem. As you see, again, the integral of u dv is equal to uv minus the integral of v du. Let's go ahead and figure out here the v quantity. It turns out you can integrate sine of x dx as easy as negative cosine of x. And you can also find du from x squared simply by what? The power rule. So du is equal to 2x dx. Turns out then you can nicely see here that u times v, x squared times negative cosine of x, minus integral of v du, so minus the integral of, so we've got 2x dx, but also negative cosine dx to be plugged into our appropriate v du integrand, which I did. But as it turns out, because we only technically wanted positive 2x dx, I applied, and the negative, of course, from the cosine, I applied a negative here, but also changed its sign out in the equation that you see here. From here, or part of the equation, excuse me. From here, well, let's go ahead and take a look. This quantity is perfectly good. Well, this quantity we do have to manipulate, yet again, by integration by parts. So from this particular integral, we can identify that u we'll call 2x dv cosine x dx. So yet again, another process of integration by parts unfolds. You could find du pretty simply, it's 2 dx. And then you can also find v by integrating cosine of x dx, which you can see here as sine of x. And then you can go ahead and plug things in accordingly. uv, so 2x sine x, minus, again, the integral now of v du, which we again have as sine of x, but the du is 2 dx. So combined, this is your integrand. This can now be integrated. So we see here 2x sine x minus, factor out the 2, integral sine dx, of which lends itself to the following: 2x sine of x plus 2 cosine x plus c. Now you're not quite done, right? That second result paired with this first part of the first result, as you can see here, says 1 and 2 combined equals x squared times negative cosine of x plus 2x sine of x plus 2 cosine of x plus c. So let's move on. We'll take a look at example 5. We are going to skip example 6, but we will finish up with example 7. Find the integral of secant cubed x dx. We're going to let dv equal secant squared of x dx, keeping in mind that even though it's secant cubed x dx, we're going to be able to use integration by parts in a simplistic or more simplistic manner. As it turns out, maybe we'll calling u secant and calling dv secant squared dx, as you're about to see. Some nice integration techniques unfold from there. So there's your u, secant of x. There's your dv, secant squared dx. The integral of secant squared x dx is tangent x, which is certainly more ideal than other options that we could have tested. Du, the integral, or excuse me, the derivative of secant is simply secant x tangent x dx. So again, here's our goal, generally speaking, using the integration by parts theorem. We got here u, so secant of x, tangent x, minus, that's your v, minus the integral of v du. Again, we said v was tangent. Technically, tangent times tangent ends up being tangent squared. The secant stems from that part, the du, partly secant of x. So combined, v du is secant tangent squared dx. A really nice thing to apply here in context is that tangent squared using a Pythagorean identity takes shape like so. It takes shape as secant squared minus 1. Moving on, we are going to go ahead and then I rewrote secant cubed x dx just to highlight the fact that, again, from the very beginning, we're still noting secant of x, tangent of x, again, that's u times v, but minus this integral split up as such. If you distribute the secant, you get secant cubed x dx, but also again, but to the negative 1, technically with this minus distributed to both integrals here, the second integral becomes a positive, minus a negative, a positive, and that's secant of x dx. Interestingly enough, this is a really ingenious step actually, because you have a secant cubed dx here. And remember the beginning of the problem involved secant cubed of x dx. What we do is we add secant cubed x dx, the integral of secant cubed x dx, to both sides. So now you have on the left side 2 secant cubed x dx, on the right side secant tangent plus integral of secant dx. You can continue by integrating the secant of x dx as such, natural log of secant of x plus tangent of x plus c, and that's the absolute value. But then we can essentially divide both sides by 2 or multiply by a half to finally end up with 1/2 secant tangent plus 1/2 natural log absolute value secant x plus tangent of x plus c. Certainly a more involved process than what we've seen thus far, but it works well in the sense that we had integration by parts for sure to take on, but also trig identities. But more impactfully, I believe, I would argue that this step right here, you got to be very, very kind of, I guess you could say mindful, but also clever in the sense that there's no other way to really get secant cubed x dx by itself, at least with this particular function in mind. Like I said, we're going to be skipping example 6. And moving on, it says here, as you gain experience in using integration by parts, your skill in determining u and dv will increase, like anything. The next summary lists several common integrals with suggestions for the choices of u and v. So just a summary here, some common integrals. For integrals of the following form, integral of x to the n e to the ax dx, or the integral of x to the n sine of ax dx, or lastly, similarly to the second but cosine, you're going to let u equal x to the n and dv equal e to the ax power. Sine ax dx or cosine ax dx for those second two integrals. As a rule of thumb, this will work out more advantageously if you do that. For integrals of the form integral of x to the n natural log dx, that I'll just speak to, we're going to let u equal natural log of x, arc sine of ax, or arc tangent ax, while we let dv equal x to the n dx. It will be, again, more advantageous if you do it that way. And lastly, number 3, integrals of the following form, integral of e to the ax sine bx dx, or integral of e to the ax cosine bx dx. We'll let u equal the trig part of the expression, sine bx, or cosine bx for that matter, while dv will let equal e to the ax dx. Let's take a look. In problems involving repeated applications of integration by parts, a tabular method illustrated in example 7 can help to organize the work. This method works well for integrals of the following form. So you've got this again, so the trig function you can see, the next x to the integral of x to the n cosine ax dx, and so on. The last integral, again with x to the n e to the ax dx. Okay, so using the tabular method, here's how it's going to look. So what we'll do is in finding the integral of x squared sine 4x dx will let u equal x squared. Therefore, the remaining part there, the dv that is, ends up being sine 4x dx. So I would certainly argue that it looks like what we see up above, integral of x to the n sine of ax dx. And because we've assigned our u and dv, what we're then able to do is we're able to set up a little table. So this little tabular approach, there's going to be alternating signs that we apply. There's going to be u derivatives and then dv integrals. So here's how it works. The signs will alternate accordingly, positive to negative, but only because of the nature of what happens, well, as you'll see here with the derivatives. So the u derivatives, starting with u as what we know it to be, x squared, going up, let's just call it a first derivative degree. It's just the first derivative. 2x, the derivative of that, 2, the derivative of that, 0. And that's where we're going to stop, at least for the u derivatives. When we do our dv integrals, we can most certainly take the integral of sine 4x dx. And if you do that, you'll get negative a fourth cosine of 4x. Take the integral of that, you'll get negative a 16th sine of 4x. Take the integral of that, you'll get 1/64th cosine 4x. A couple things to note as far as these signs go. So we do this kind of in a diagonal manner in which we actually take the u derivative times the dv integral. So you can see here, if you take x squared times negative 1/4 cosine 4x, there's the first term in your resulting expression. And you continue on. And by the way, that sign stays positive because technically the alternating signs translate in that particular way. So multiply across, and there you go, on a diagonal. Again, multiply on a diagonal, 2x times negative 1/16th sine 4x. Noting the sign change, okay, it's going to be a negative of a negative, so positive, we get what? 1/8 x sine 4x. And then last but not least, 2 times 1/64th cosine 4x. The sign does in fact stay as positive. So 1/32nd cosine 4x plus c.